Welcome to the video on vapor pressure diagrams. Alright, so we've already examined the phase diagrams for one component systems, and now we're going to examine the phase diagrams for two component systems. So such a phase equilibria are more complex because the composition is an additional variable, so we can change the composition in addition to the pressure and the temperature, or other variables. But they can still be useful summaries of phase equilibria for both ideal and real systems. Alright, so the partial vapor pressures of the components of an ideal solution of two volatile liquids are related to the composition of the liquid mixture according to Raoult's law. So note that in the last video we were looking at an ideal solution or real solution of a volatile liquid with a non-volatile liquid. So here we're going to look at two volatile liquids. Raoult's law says that the vapor pressure of component A is equal to the mole fraction of component A times the vapor pressure of component A while it's pure, and a similar expression for B, component B. So the total vapor pressure, P, of the mixture is then the sum of the two, so P is equal to vapor pressure of A plus the vapor pressure of B in solution for both of them. And from the last slide, that means that now we have this expression, so the mole fraction of A times the vapor pressure of A when it's pure plus the mole fraction of B in the mixture times the vapor pressure of B when it's pure. And we also know that the mole fraction of B is 1 minus the mole fraction of A, because again we only have two components in the mixture. If we have more than two components, then this isn't true, but it's true as long as we have two components, which then means that the pressure is equal to this, and after some math we can then simplify that to the total pressure is equal to the vapor pressure of B when it's pure plus the mole fraction of A times the quantity of the difference between the vapor pressures. So this means that if we, this means that the vapor pressure, the total vapor pressure varies from the vapor pressure of pure B, right, if the mole fraction of A is 0, to the vapor pressure of pure A, where note that if the mole fraction of A is 1, then we have the vapor pressure of B plus 1 times the vapor pressure of A when it's pure minus the vapor pressure of B when it's pure, so those two cancel, no adjustments with the vapor pressure of A. So that means that if we look at a plot of the vapor pressure, the total vapor pressure above the mixture, as a function of mole fraction of A, we go from the vapor pressure of pure B at a mole fraction of A of 0, which means we have pure B, all the way up to the vapor pressure of A when it's pure at pure A, right, at a mole fraction of 1. And in between, it's just a linear relationship between the two. So this means now the composition of the liquid and vapor in equilibrium are not necessarily the same. The vapor is enriched in the more volatile component. So in the last slide, A was the more volatile component. So remember, the partial pressures are given by this equation. So Pj, where Pj is the partial pressure of the component J. The partial pressure of component J is equal to the mole fraction of J times the total pressure. And from Dalton's law of partial pressures, then we can say that Y of A, where Y of A and over here Y of B are the mole fractions in the vapor phase. So this is basically chi A, but where here Y refers to the vapor phase. So we're going to talk about chi A as being the liquid phase and YA as being the gas phase mole fraction. So here's the liquid phase mole fraction, and here's the gas phase mole fraction. And similarly for B, we have chi B, which is the mole fraction in the liquid phase, and YB is the mole fraction in the gas phase, in the vapor phase. So we now know that the mole fraction of A in the gas phase is equal to the partial pressure of A divided by the total pressure, that's the mole fraction, and likewise for B. So if the mixture is ideal, then the partial pressures and the total pressure P can be expressed in terms of the mole fractions in the liquid. So the partial pressure of A is equal to the mole fraction of A in the liquid times the vapor pressure of A when it's pure, and we get a similar expression for the vapor pressure of B. Well, that means that the total pressure in of the vapor phase is equal to the vapor partial pressure of B when it's pure, vapor pressure of B when it's pure, plus the mole fraction of A times the quantity that is the difference between the two vapor pressures while they're pure. And that means that now we get this big expression. So now the mole fraction of A in the vapor phase is equal to the mole fraction of A in the liquid phase times the vapor pressure of A when it's pure divided by this guy, because that was the pressure. And then the mole fraction of B is 1 minus YA. So this expression here. So this plot on the right shows the composition of the vapor. Here, this is the mole fraction of A in the vapor phase, so that's YA, as a function of the mole fraction of A in the liquid phase for varying values of the ratio between the vapor pressure of A when it's pure and the vapor pressure of B when it's pure. Note that we're fixing these as greater than 1, so we're saying A is the more volatile component. So if the vapor pressure of B becomes larger than the vapor pressure of A, well then B is the more volatile component, so we switch our labels of A and B. So we're only looking at values for this fraction of greater than 1. So at a fraction of 1, that means that A and B are equally volatile. They have exactly the same vapor pressure when they're pure, which means that whatever the mole fraction of A, it just has, the vapor phase has the same ratio as liquid phase does, because there is not a more volatile component. If the vapor pressures of A and B, if that ratio is 1, that means the vapor pressure of pure A and the vapor pressure of pure B are the same. That means that they're going to volatilize at the same rate, so the mole fraction in the vapor phase will be exactly the same as the mole fraction in the liquid phase. But as A gets more and more volatile compared to B, the vapor phase gets more and more enriched in A, the more volatile component. So, again, noted that in all cases our vapor is enriched in the more volatile component, with the possible exception of the two being the same, but then we don't really have a more volatile component. So if B is non-volatile, then the vapor pressure of B is 0, which means that, or at whatever temperature we're looking at least, and that means that the mole fraction of B is 0, which means the mole fraction of A must be 1 all the time. As long as we have any A around, then it will, some of it will be in the vapor phase, and that's all that's there. Because if we don't have any B in the vapor phase, then 100% of the vapor is component A. So that's why this is trending towards a mole fraction of 1, even at really, really small quantities of A in our mixture in the liquid phase. So we can now relate the total vapor pressure to the composition of the vapor. And so now we can say the total pressure is equal to the vapor pressure of A when it's pure times the vapor pressure of B when it's pure divided by the vapor pressure of A when it's pure plus the mole fraction of A in the vapor phase times the quantity vapor pressure of B when it's pure minus the vapor pressure of A when it's pure. So that's the same expression we have here. So that expression is now plotted on the right. So now we have the total vapor pressure plotted here as a function of the pressure as a fraction of the vapor pressure of A when it's pure, as a function of the mole fraction of A in the vapor phase. So, as we get down here near near zero, of course the mole fraction or the total vapor pressure is lower, but it's still not linear, you notice. It's still not going all the way down to a vapor pressure of zero as it would be for if B is a non-volatile component. Alright, so if we're going to look at distillation, that means that both the composition of the vapor and the composition of the liquid are important, and this means that we want to be able to combine both on a single plot. So over here we have a plot of the pressure as a function of the mole fraction of A, and here we're calling this ZA. Okay? And so now we want to put these on the same plot. So the liquid is up here, the vapor is down there, and we've got some region in between. Right? We've got a couple of lines there we're going to talk about. So point A, that's this point here, indicates the vapor pressure of a mixture with composition chi A. Right? So that's this one. And point B represents the composition of the vapor that is in equilibrium with that liquid at that pressure. So if we have some liquid at this ratio, this mole fraction at point A, the vapor phase above that is along this line, and that's at point B. So note that the vapor phase is enriched in component A. Component A is the more volatile component. We know that because the vapor pressure of the whole solution at mole fraction of A of 0, so pure B, is down here, and on the other end we've got the mole fraction of 1 of A, mole fraction of A of 1, and that gives us a vapor pressure of pure A, and that's up here. So A is our more volatile component. So note that we can change our horizontal axis, so the bottom axis here, to be the overall composition of the entire system. So now we're no longer talking about the mole fraction of the liquid or the mole fraction of the vapor phase. We're talking about the mole fraction of the whole container. Both the liquid and the vapor phase combined into one number. That's this ZA that we're talking about. Right? So that's the mole fraction of A of the whole system, the chi plus Y. Alright, so all the points at or above this solid diagonal line represent a system at such a high pressure that only the liquid phase exists. If we put our system under high enough pressure, then we'll condense all of our vapor phase back into a liquid phase, and we won't have any vapor phase at all. And so that's what we're talking about. And in that case, if there's no vapor phase, then ZA, the mole fraction of the whole system, is equal to chi A, the mole fraction of just the liquid. There is no vapor phase, so they have to be equal. All the points below the lower curve, so below this blue line, represent a system at such a low pressure that only the gas phase exists. We've vaporized all of our liquid, and so now our total mole fraction of both the liquid and the gas phases combined is just the vapor pressure of just the mole fraction in the gas phase, because we have no liquid phase left. We've vaporized all of it. So that's everything below the line, not including the line. And likewise, for the liquid phase, that was just above the line, not including the line. At the two lines, or in between the two lines, so points in between our two curves represent a system in which both our gas and our liquid phases are present, both the vapor and liquid phases exist. And so now let's consider the effect of lowering the pressure on a liquid mixture of overall composition A. So we're talking about this point here. So we're starting out here, and we're at relatively high pressure, and we're going to slowly lower the pressure and watch what happens. We're going to lower it down here. So the overall composition doesn't change. ZA is constant, right? We're not getting off of this dotted line. We're going to stay along that dotted line. The total composition is changing, but the composition of our two phases may be changing, and that's what we're going to look at. So this means that the state of the system must move down our vertical line through A. All right, and this line is called an isopleth, for the Greek for equal abundance. Right? So we have the same mole fraction of A in the total between the two phases. So that's our isopleth that we're going to move down. So as we go from A to A1, so that's from here, this point, down to this point. So note that A1 is on this this red line. So this is pressures above P1. So for pressures above P1, the system is entirely liquid. And it's only once we reach this red line along our isopleth that now we get some vapor phase forming. So at A1, at point A1, the liquid is in equilibrium with the vapor. And this means the composition of the vapor is now at point A1 prime. So the composition of the liquid is here. And once we start to vaporize some of our liquid, that vapor is at this other composition. So is that enriched in A or enriched in B? That's enriched in A, right? We have a higher mole fraction of A in our vapor phase, and so we've now purified A for the vapor phase compared to the liquid phase. So now let's look what else we can do. All right, so this line, this solid black line connecting the two, that line right there, that's what we call a tie line, connecting our two phases together. All right, so the composition of the liquid is the same as the starting value. That didn't change. So that must mean that there's virtually no vapor present. Because if we push more of our vapor to this composition, then we're going to be removing, remember we're enriching the vapor in A, which means we must be enriching the liquid in B. But if we haven't actually changed the composition of our liquid, that means that we must not really be enriching it in B very much. It means we can't have very much of our vapor phase. So there's not much of our vapor phase actually present. But if we lower the pressure now a little bit more, now we get to point P2, so that's this pressure here. And now our overall composition is represented by this point, A1 double prime. So that's not supposed to be 1 double prime, that's supposed to be 2 double prime. So that's this point here. That's our overall composition of the whole mixture, because we have to stay along this isopleth. But our liquid phase is no longer at that point. Note that our liquid is vaporizing until the vapor pressure of the resulting liquid composition falls to P2, which means here. There. So the liquid composition is now at this point over here. So we've now enriched our liquid in B. We've removed some of the A from it, but that means that we've also enriched our vapor phase in A. So that means that the liquid composition is now A2, that's this point, and the vapor composition is now A2 prime, so this point. So our liquid is getting enriched in B, the less volatile component, and the vapor phase is getting enriched in A, the more volatile component. So let's keep going. Let's lower our vapor pressure, lower the total pressure to P3, so that's this point. So now the composition of the liquid is at A3, so we're over here. For the liquid, we're even more enriched in B than we were at pressure P2. And that means that the vapor, the composition of the vapor is at A3 prime, that's here. note that now the composition of the vapor is equal to ZA, which means that there must be virtually no liquid present. We've basically boiled all of our liquid. So yeah, we've enriched our liquid in B, but we've returned our vapor phase back to the total composition, which means pretty much all of it is in the gas phase. So we've basically just boiled everything. So everything that was in the liquid phase, now it's all in the gas phase, right? And now we've actually reached down here our blue curve, right? Point A3 prime is on that blue curve. So we're on that curve. So the relative amounts of the phases, let's go back a second. So if we continue going down, if we get to a lower pressure down here at A4, that's just all vapor phase. We've basically just decreased the pressure. Right? We've expanded our container some, but the composition is still the same. Right? The gas is just expanding now. Right? Because once it's all vapor, it can't go anywhere else. Right? It's just going to expand into the extra volume that we have. All right, so let's look at the lever rule. So the relative amounts of the phases in the two-phase region of a phase diagram, so that's this region in here, that region in between those two curves. So the relative amounts of the phases in the two-phase region of a phase diagram can be determined using the lever rule, right? Where now we have Na, so Na is the amount of phase A, so the number of moles of phase, or phase alpha, times, and then N beta is the number of moles of phase beta, so say liquid and gas. This is, so then La, so this value here, that's the length of a portion of the tie line on the alpha side of the isopleth, and Lb is the length of the portion of the tie line on the beta side of the isopleth. So let's look at what exactly we mean here. So suppose we take a system and we have it initially at equilibrium. So we have some liquid phase down here in this green, and we have some vapor phase up above it, and we pull up on our plunger, and we have more of our gas phase now. Well, that means that our liquid phase must be decreasing some because we're vaporizing some. If we keep going, then eventually we'll have all vapor phase. So we're going to look at this one, and we're going to look at this one. So on this side, we now have the pressure as a function of composition. So just like we had a couple of slides ago, only in this case now we've blown up a portion of it. And you can see here we have our liquid side. Up here is liquid, and here we have our blue curve representing the gas phase, and down there is our gas. So here is beta, that's our beta phase, and here is alpha, that's our alpha phase. So alpha in this case may be liquid, and beta there may be gas, beta phase. So whatever the overall composition is, that's that point, or that line, that isopleth. We have some point on that line, and that LA, L alpha, is the distance between this point and the midpoint there, not the midpoint, the point on the isopleth. And LB, L beta, is the distance between this point and the point on the isopleth. So for this figure that we show over here, L beta is about double L alpha. So that means that the number of moles of alpha have to be about double the number of moles of beta, which means that there has to be about twice as much alpha as there is beta. So think of this like weights. Right? We've got a weight here sitting at this point, and we've got a weight there sitting on that point. If we have a fulcrum here at the isopleth, well, if this lever is twice as long as that lever, then the weight, to keep these balanced, the weight on the left side, on the shorter side, must be bigger than the weight on the right side, the longer side. Which means that we must have more of phase alpha than we have of phase beta. So that's why this is called the lever rule, that it acts sort of like a lever, like a balance. So that was vapor pressure diagrams.